Well, good morning. As I was already introduced, I'm Evan Davis. I'm with the MIT Plasma Science and Fusion Center, and I'm going to be talking to you this morning about some calculations I've been doing of stability and turbulence in tokamak fusion reactors. And before beginning, I just wanted to let you all know how excited I am to be giving this talk, because for the past 4 years at all the poster sessions, I don't think anybody has stood around long enough for me to actually explain all of my research to them. But you guys are stuck with me for the next 30 minutes, so pay attention. Just as an outline, I'm just going to be talking about some basic fusion background, just so we kind of all get on the same level playing field, discussing some basic reactions of interest, and some requirements for a power-producing reactor. I'll then go on to Tokamaks, what they are, how they initiate fusion, and what currently limits their operations. I'll go into some details of the tokamak I'm actually modeling, which is MIT's Alcator CMOD tokamak. I'll then be talking about some modeling, giving you a brief overview of the equations we're using and some physical intuition we can use to predict what we expect to see. I'll be talking about some linear stability calculations and then move on to some nonlinear turbulence, showing both what the code does well and what it does poorly with regards to matching experimental measurements. And then I'll just end with some conclusions and future work. So just starting off, I think this is a curve we're probably all relatively familiar with. It's the plot of average nuclear binding energy per nucleon versus atomic mass. As we know, going from the right all the way left, you're splitting heavy atoms, doing fission, releasing energy via Einstein's E equals mc squared. And fusion, what I'm interested in, is taking isotopes from the low mass section and bringing them together to release energy. Obviously, as we also know, this is also a very hard thing to do because these nuclei are very, they don't like to come together because they're positively charged. So the thing that we would like to do to kind of choose our fusion fuel is choose the fuels that will have the highest reaction rates. And the one that is kind of the prototypical fuel for a first-generation type fusion power plant is fusing deuterium and tritium. This produces a alpha particle and a neutron and releases 17.6 mega electron volts. And the reason why that is you can see the reaction rates over here, reaction rate on the y-axis versus temperature. And the temperatures we're kind of interested in our reactors is around 100 million degrees Celsius, around right here. And here you can see the deuterium-tritium line, given by this blue curve, is around, you get a reaction rate, roughly 100 times larger than any of the nearest competing reactions. Tritium, though, as most of us probably know, is radioactive. And running a plant with 50-50 mix of deuterium and tritium makes you into a nuclear facility, and the cost and complexity of your reactor goes up roughly an order of magnitude with that. Fortunately, the physics of just fusing deuterium and deuterium together is about the same, and so these are the reactions that typically are happening inside these power plants that we're studying today. So one of the criterion that we can set for a power-producing reactor is something on this fusion triple product of N, T, tau, E. So what this is N is the density of your fusion fuel. Obviously, the denser it is, the more likely you are to have a fusion reaction. Temperature corresponds to how energetic your particles are. The more energetic they are, the more likely they can overcome that Coulomb barrier and fuse. And finally, this tau E is the energy confinement time of your reactor. And that basically says if you withdraw the heating source you have to heat up this plasma and cause your fusion reactions to occur, how long does your device hold on to this energy? And we can set a very basic limit on this triple product to achieve what we want to, this ignition, which is the point when the fusion byproducts, such as those alpha particles we saw on the previous slide from the deuterium-tritium fusion, are sufficiently contained and energetic to just heat the plasma without you needing to continue injecting external energy into it. And the limit we can that was derived long ago is just you balance this energy released via the DT fusion with Bremsstrahlung emission, which is just emission from the accelerating electrons in your plasma, and you get this limit, a minimum bound of 4.7 atmosphere seconds. And what that means is, let's say you have a plasma and it's up to a pressure of 4.7 atmospheres, you'd have to have an energy confinement time on the order of a second. Where we get pressures in our devices today on that order of an atmosphere, the energy confinement time isn't of that second length that we need. It's more on the order of tens to hundreds of milliseconds. But just so you can see exactly how much we've progressed over the course of fusion history, we have this plot here, and this shows several different technologies, blue being a magnetic confinement fusion reactor. Red is number of transistors, like per area, and green is accelerators. And the important measure here is this dashed line, which is where you'd reach this ignition point. And you see we haven't quite reached it, but we're quite close. And the other thing that's pretty important is this slope of this line is actually exceeding that of the transistor number, which tells you that this triple product has actually outpaced Moore's law, which is quite impressive. So what are we doing fusion in? The leading kind of concept for a magnetic confinement fusion reactor is this Tokamak. And this was a Russian innovation, so the word itself, it sounds kind of funny, but that's because it's an adaptation of a Russian alliteration for a word meaning toroidal chamber with axial magnetic field. That sounds pretty dry, but maybe a picture does a little bit better, a little more justice to what this actually is. So it's a torus, or a donut-shaped device. You can see it wrapping around here. And it's characterized by these very large magnetic field coils that produce a very large so-called toroidal magnetic field that wraps around the device in the axial direction. Then you can put in a plasma into this device. Your plasma is just an ionized gas, so this field acts to confine the plasma. But it turns out that this purely toroidal magnetic field, although it has very good stability, it actually won't allow you to develop a good equilibrium. And what you need to do to get a good equilibrium in your plasma is also produce these so-called poloidal magnetic fields that wrap the short way around the donut. And you do this by just driving a very large current through the plasma. And that gives you these kind of characteristic corkscrew field lines that you see in black that allow you to get good stability and good equilibrium. Just so you see exactly where we kind of sit with regards to other, in the parameter space, I've included this plot. There's density on the x-axis, temperature on the y-axis. And Tokamaks are sitting right here at around 10 to the 14 cubic meters, or cubic centimeters, and temperatures of order 100 million degrees Celsius. You see kind of our familiar ICF plasma sitting kind of right next to it, but the plot is kind of deceiving because there's really 4 or 5 orders of magnitude density difference between these two. And you can just also see the very rich diversity of parameter space that these plasmas can occupy, and just tells you just how rich plasma physics can be. So now I kind of want to just tell you, give you a brief overview of the Alcator C-mod tokamak, which is at MIT and the tokamak I'm actually modeling. And it's, in my opinion and many other people's, uniquely poised to address many reactor-relevant issues. The first is that C-mod, its real claim to fame, is that it is a compact, high magnetic field tokamak. And so what that means is it's small and it uses very large magnetic field, up to 8 Teslas. And just so you can kind of see where it occupies, where it sits in this parameter space, I've made a plot of all these dots correspond to various tokamaks that have been built or are planned to be built in the near future. On the x-axis is the major radius or size of the device, and on the y-axis is the toroidal magnetic field. And C-mod sits right here at this red dot. So you can see it's on the smaller side with also a very high magnetic field. This is important because the confinement, this n tau e, which is 2 components of that triple product that you need to exceed some minimum criterion of to make energy, it scales with b cubed. So having a high magnetic field allows you to get good confinement, and the cost also scales roughly as the volume of the device, or r cubed. So keeping that small is important for making these things economical. C-mod also has all metal plasma-facing components. You can see that with this shot in vessel of the device. You can see here's kind of this torus-like shape and all these metal tiles. They're molybdenum. This is important because in a reactor, you can't be using something like carbon, which most devices use today, because it has very high tritium retention. And using metals substantially reduces that. But it also substantially changes properties on the edge of the plasma, and that really needs to be studied, which you can do on this reactor. It has reactor-relevant particle densities and heat fluxes of order 10 to the 20 cubic meters, and parallel heat fluxes of order 500 megawatts per meter squared. You can see kind of a discharge in development here. This is, thousands of degrees, and you can see this visible light emission. And it turns out the hottest part is right here in the core, and it's so hot, it's X-ray hot, you can't see it with just normal visible emission. But it's of order 100 million degrees Celsius in here. Finally, CMOD is always very strongly relied on the graduate student population. There's generally 30 or 40 graduate students who work on this, and really the device just wouldn't run without them. And these are the people who would be working on these next generation reactors. And one of the most exciting things that's happened, or definitely most important discoveries since Tokamaks have been researched, is a discovery of this H-mode operational regime, which stands for high confinement. And the idea here is pretty easily summarized with this plot, which was just taken from the original H-mode paper. And on the x-axis, you just have power that you're pumping into your plasma. And what you'd expect is that as you pump more power in, the pressure of your device would go up. And that's exactly kind of what this line here with these filled black circles is indicating. That's saying, this is kind of the default mode of operation most Tokamaks were operating in. But they found out if they tweak the plasma and it's shaped just right, there's this minimum power threshold where the behavior bifurcates, and you get this huge jump in pressure and also a corresponding increase in the energy confinement time. And this is, so important that it is now kind of the baseline operational regime for all future reactors. So if you want to kind of understand what's going on here, you can look at the profiles of density and temperature in a tokamak during H-mode. And that's kind of what this plot here is trying to indicate. So on the x-axis, we just have radial position inside the device, 0 being the core where it's the densest and hottest, and 1, this is out towards the edge. This is just some normalized radial coordinate. On the y-axis is just your density or temperature. In L mode, you just see a kind of nice smooth decrease towards, reaches 0 out towards the edge where you kind of make contact with the walls. But in H mode, what actually happens is right here in this edge region, right here, you get a substantial reduction of turbulence, and you develop this so-called transport barrier. And as a result, you get this large pedestal with very steep gradients building up. And this, in turn, just lifts up this whole L mode profile and allows you to achieve much higher temperatures and densities in the core. And this is important because the reaction rate, sigma v, in this temperature range of interest roughly scales or is dominated by this exponential factor. So increasing the temperature will allow you to get an exponential increase in the rate of your reactions. So the rest of my talk is going to be talking about this edge region and focusing on how we can understand this and how that dictates the properties of our tokamaks that we are looking at. So it turns out, while H-mode is great, you get good energy confinement, you get good performance, it also in some cases is just a little bit too good. And that's seen here. This is something called an edge localized mode. It's basically this filamentary-like explosive instability in the edge of the tokamak. And these occur because you also start getting impurities in your plasma that are just kicked off the wall of the device. It's in contact with something that's thousands of degrees, so you're getting some sputtering, some melting, and all these impurities can get into your plasma. And these impurities are generally much higher Z. They can radiate your energy away and just make a complete radiative collapse of your plasma, which is bad. So what these ELMs do is they just kick these impurities out. And it's all, well and good in current reactors that are, small, such as CMOD. But if you scale these up to a next generation reactor like ITER, I've heard, quotes of it basically being like setting off a grenade inside of your device every few milliseconds, which is just not good. So there's been a lot of work, both from the experimental and theoretical perspective, trying to understand where these things come from and what, how we can maybe control or suppress them. And it's been a huge success from theoretical plasma physics in the last 10 years or so to show that these ELMs are actually dictated by ideal magnetohydrodynamics, or ideal MHD, peeling ballooning stability theory. And what that means is, this is just a simple sketch. If you have this large pressure gradient in the edge, if you exceed some critical pressure gradient, you become unstable to these so-called ballooning modes. And if you have too much current in the edge of your plasma, you become unstable to these peeling modes. But you can sit in this kind of happy medium in here, and if you are here, you're not going to trigger an ELM. But not all H modes actually exhibit these ELMy type instabilities. On CMOD, the kind of workhorse H mode that we see is the enhanced D alpha, or EDA H-mode, and this has a edge fluctuation called the Quasicoherent Mode, or QCM. It's this, you can see a power spectra here, and this is this roughly 100 kilohertz oscillation that's relatively coherent, and instead of these kind of periodic ELMs that are very explosive, this is a very benign fluctuation that does the exact same thing. It just kicks those impurities out and allows you to reach a steady state, which you can see in these plots. You see a density trace, you're in L mode here. You enter H mode, it kicks up, and you reach a high confinement here. But your radiated power here stays relatively low because you're kicking out all those impurities. This regime of operation is also relatively collisional, so we can use fluid models to try and understand what's going on here. And the first thing we can do is just see how it compares to that ELMy kind of standard model we saw on the previous slide. And here, these are actual calculations from an ideal MHD code. This green boundary here is the stability threshold. The operational point is right here, very far away from this threshold. So that tells you these are, one, they're not ELMs, and two, they aren't ideal MHD modes. So it's something else, and we would like to figure out what exactly is it that is giving rise to this fluctuation and what's constraining this operational regime. So one of the most natural things you can go to is look at a non-ideal version of MHD, and that's what we've chosen to do here. And you can include several effects such as resistivity, these Hall physics, which corresponds to this parallel pressure gradient effects, and diamagnetism. And some of these, such as the resistivity in particular, we think would be very important for the relatively collisional plasmas in Alcator CMOD. Just to walk you through these equations real quick, this is a vorticity equation, and it just tells you this evolution of the vorticity is governed by two terms. This peeling drive we had talked about before, driven by currents, and a ballooning drive driven by pressure gradients. And it turns out in CMOD, the pressure gradients are actually the most important drive for instability. The pressure evolution is just a simple advection by plasma velocity, and you have this Ohm's law, which includes a lot of the non-ideal effects. Before getting into the results, I just kind of want to talk a little bit more about what the ballooning drive is, since that is the dominant mechanism for instability in CMOD. And you can imagine you have a plasma here, this kind of orange diffuse gas, and you're using magnetic fields to confine it. So these fields are just wrapping around, and they are decreasing in strength as you move radially outwards. As a result, you have your curvature vector for your field is pointing radially inwards, and your pressure gradient is also pointing radially inwards. Now imagine you have some sort of instability. It starts right here, and it moves outwards. As it moves outwards, it's going to experience a weaker field, and this field is going to be less and less able to push this instability back into the plasma. And as a result of that, it's kind of a little bit of a runaway type reaction. It'll allow itself to keep growing. So we say this is bad curvature when the curvature and pressure gradient are aligned. In contrast, if you have this kind of cusp-shaped magnetic field, you see that if you move radially outwards, the field density increases, and it's going to be more able to push this plasma back in radially if it moves out. And this is so-called good curvature. So what does this look like in a tokamak? Here we have just a cross section. You have the devices just wrapping axially around this axis here. And the curvature, since the field is predominantly toroidal, is always pointing radially inwards towards the center of this donut. In contrast, the pressure gradient points always radially inwards towards the core of the plasma. So over here on the inboard side, you get good curvature. On the outboard side, you have bad curvature. And because of that, we expect to see these ballooning instabilities kind of on this outboard side of the tokamak. And we'll see that's exactly what we do see. So these are some linear stability scans we've done to investigate exactly what could maybe cause this quasi-coherent mode oscillation. And the 2 points of interest on these axes are the values of unity. So here on the x-axis of a value of 1, this is the experimental pressure gradient that this is measured, and this is what was input into the code. On the y-axis, we have growth rates, and the value that really matters is, again, unity, and that's because if you exceed this value, you'll trigger some sort of instability. If you're below it, there is this suppression mechanism in the plasma that will keep it from becoming a real instability. And this blue curve just shows these ideal MHD calculations. This is with a different code than we saw, than I showed previously, but we get essentially the same result. At the experimental pressure gradient, we're very far from instability, so we don't expect to be seeing any sort of ELMing activity. In contrast, if we start including these non-ideal effects, such as resistivity, you get this green curve here, and you see the stability properties have dramatically changed. In particular, right at this experimental pressure gradient, you're right at this stability threshold, which says you're right about to trigger this instability. So this is it seems like this could be a resistively driven mode that is responsible for this quasi-coherent mode oscillation. You can look at the cross section of the device with this instability. You can see exactly what it looks like. And you see, kind of like we were expecting with this ballooning drive, you see this instability is predominantly localized and strongest in this outboard side. And we call this instability resistive ballooning mode. And that may explain, at least linearly, where this mode is coming from. We can then move on and do some nonlinear calculations. And you see a lot of features that are actually very similar to what we observe experimentally. In particular, we have this power spectrum here. And you see this nonlinearly driven, relatively coherent oscillation around 400 kilohertz. And it propagates in what we call the electron diamagnetic direction of the plasma. And this is, very reminiscent of what we see experimentally. The actual mode in the experiment, it does propagate in the electron diamagnetic direction. It's relatively coherent, and it's, fluctuation frequencies on the order of 100 kilohertz. So it looks like, we might be getting something kind of right. You can also look at the profiles here. You see the radial domain here. And this is the equilibrium profile. This is the fluctuating mode structure. And it spans this edge region just like we see in the experiment. It has a experimentally relevant amplitude of 20 or 30%. You can also look at the poloidal wave number and the power contained in where the dominant wave number or most power is. And you see that's this blue trace, and the power is predominantly localized at around 2.25 inverse centimeters, and that compares very favorably with what we see experimentally, which are these red bars. So macroscopically, it looks like we're doing a great job. However, we can look a little bit more in depth. We can look at the phase relationship between these instabilities. This red curve shows the electrostatic potential. Blue shows the pressure. And you see they're out of phase. And this is exactly what you'd expect with a ballooning mode. However, some very recent measurements were done with a novel probe. And you see that the density and electrostatic potential are actually much more in phase, which is indicative of a drift wave, which is a totally different instability. So it seems like we were doing good, but apparently, at least in the microscopic physics, it seems like things are just not quite in agreement. So something we could try and do is add in this Hall term, this pressure gradient effect, into Ohm's law and see if that gives us what we would like to see, this drift wave-like relationship. This is just the previous stability plot we saw, and if you overplot the stability when you add in this drift wave, or this Hall term, we get this red curve. And again, it just sits right at that stability threshold. Things don't really change much in the linear perspective. But if you look at the nonlinear evolution, things change dramatically. Green is what we had seen before. This is just the time history. This is the size of the pressure perturbation versus time. And the red curve shows the simulation with the Hall term included. And you see it kind of has this extremely fast period exceeding what the linear growth was in the old simulation. And it reaches nonlinear saturation much earlier. So we would like to understand why this happens. You can look at this frequency spectrum. Green is, again, just resistive. Red includes resistive and Hall effects. And you see that the Hall term seems to drive more high-frequency turbulence that could produce more efficient cascades and potentially explain the differing time series. Unfortunately, the phase relationship is still off, so we don't get that drift wave-like relationship. And we may need to move to a two-fluid model in the future to really fully capture what's going on in the experiment. So just to conclude, Tokamaks are the leading concept for magnetic confinement fusion reactors, and their performance is crucially determined by parameters in the edge of the device. CMOD has this quasi-coherent mode, or QCM, that continuously exhausts these impurities from the plasma. It's not predicted by IDLM HD, but it does seem, at least linearly, to correspond to resistive ballooning modes. These resistive ballooning modes drive nonlinear features that are macroscopically similar to the QCM, but recent measurements indicate that it is actually a drift wave rather than a resistive ballooning mode. And unfortunately, as of yet, our attempts to excite this experimentally observed drift wave in the model have not been successful, and we may need to move to a two-fluid model in the future. So I'd just like to end by thanking all of my collaborators, thanking NNSA for the financial support, as well as Krell and its wonderful staff for 4 years of just unbelievable support. So thank you.